Alright guys, so welcome back to another video. Now we are on the second last topic of our last module, advanced modeling techniques. So in this video we'll be covering neural network. This is undoubtedly one of the most powerful techniques of modeling. So let's see what we are going to cover in this video. We will first see why do we need neural network? Because we have so many algorithms available. So what makes neural network special? Then we'll see what is a neural network. After that, we'll see something called activation function in neural network. Then we'll see the cost function of neural network. And after that, we'll see the steps involved in neural network. And after that, we'll learn about the concept of gradient checking. Recall we came across this term earlier in our third module, that was modeling. So here we will learn about this concept that is called gradient checking. And then we'll also touch upon the sensitivity analysis of neural network. After that, as usual, we'll do assignments on it. So there will be 2 assignments on neural network. Okay, so without further ado, let's get started with our first topic, that is why do we need neural networks? So we have seen this earlier as well, that there are 2 forms in which we have our data, structured and unstructured. So there are different methods like regression, trees, etc. that we have learned earlier works well on structured data. But when it comes to unstructured data, their performance drops drastically. So here comes the neural network as our savior. We have neural network which can handle the unstructured data like no one else can. That is the reason this is one of the most powerful methods currently in use. Furthermore, there are instances when the number of features are very high and all features must be included. In that case, neural network outperforms other algorithms. So let me give you an example for this. Suppose we have an image of a car and we want to build a classifier which can distinguish between a car and a non-car. Basically, it can identify that it is a car by just looking at the image. Okay, so we know that an image is nothing but a grid of n cross n pixels, where each pixel has some color intensity and all pixels are collectively called as an image. So if we take out one pixel, then we know that the color of each pixel is made of the primary colors, that is red, blue and green. So now we know that each pixel can be defined by a 1/3 vector. That means if we have an image of n cross n pixels, then it will have features equal to 3 cross n square. Now let's say our car image is a 50 cross 50 pixel image. That means it has 3 into 50 square features. Now don't you think it's way too many features? And techniques like logistic regression becomes computationally inefficient here. So in situations like this, neural network comes as a savior for us. And that is why it is considered one of the most powerful techniques available out there. So now that we know why it makes sense to use neural network, it's about time that we learn it. So let's see what is a neural network. Neural network is a machine learning technique which is modeled on the human brain, and it is used to recognize patterns from the data. That is the reason it is called neural network. Neural network attempts to mimic the human brain. So we can say that there are different algorithms in human brain and our brain uses them based on the task at hand. Or we can say that it learns to do things from our experience. So the latter seems more sensible as we are not programmed human beings and we learn things with our experience. So in the same way, a neural network also learns things with the experience and it looks something like this. It has an input layer which is equal to the number of features plus one bias unit. Then we have a hidden layer. The hidden layers could be any number. In general, it is 2 to 3 times the number of units in the input layer. So hidden layer is the layer where all the calculations are performed to give the output. Then the last layer is our output layer. And the units in the output layer will be equal to the number of classes of the response variable. Now the units in these layers, which are denoted by the circles, are called neurons. So the input layer's consisting feature is also called as initial neurons. Then we have the bias unit, which is given in the input layer, and it is taken as 1. Now as far as bias neuron is considered, it is like an intercept, which helps us in adjusting the output. Now if you wish, you can read more about it, but it is not that important for us right now. So just understand that bias unit is considered as 1, and it is just customary to add it, which basically helps us in adjusting the output. Now the hidden layer has neurons, which has an activation function, where all the calculation takes place. We will see the activation function in detail, but this is just to give you an idea how this entire thing works. Also, if you have noticed, the notations that we are using are shown here on the screen. Here the number in superscript denotes the layer, and the number in subscript denotes the neuron. So here 2 denotes the layer and 1 denotes the neuron unit. So it means it is the first neuron of the second layer. So keep this notation in mind, because this is the notation that we are going to follow throughout our topic of neural network. Now the next task is to calculate the activation function. So as you can see here, each layer is connected by a weight matrix theta1, theta2 and so on. And then we apply the activation function a1, a2 up to am, which is given in the hidden layer, denoted by the orange circles. So activation function is applied to perform non-linear operations to move to the next layer. As I said, we have a weight matrix here in every layer. So we use different weights for calculating each of the neurons. We will see this in a while, how we use weights to calculate the neurons. But before that, let's understand what is an activation function. Now the activation function here is a sigmoid function. The equation for activation function is shown here. Here thetas are the weights. So there are many activation functions available, and its choice affects the performance of the model. There is one more common function known as ReLU function, which can be used as an activation function. Anyways, for now we are using sigmoid function. So let's see how do we find it for each of the neurons. So this is our neural network. The bias unit in the input layer will always have a value of 1, so we don't have to calculate it. Then the value of activation function for the input layer will be equal to the features. So again, we don't have to calculate the neurons of the first layer. Now for the next layer again, the bias neuron will have the value equal to 1. And then to calculate the activation function for hidden layer, we will use weights as shown here. Now as you can see, to calculate the first neuron of the hidden layer, we are using all the neurons of our previous layer, which happens to be our input layer. So all neurons of previous layer will be used to calculate all the neurons of the next layer. So the value of neuron can be calculated using the sigmoid function as given here on the screen. Just multiply the weights with each of the neurons of the previous layer and then add it and then use the sigmoid function. This way we'll get the neurons in the hidden layer. Similarly, to calculate the mth neuron of the hidden layer, we will multiply the respective weights with the neurons of the previous layer. So as you can see here, we have multiplied the weights with the neurons of the previous layer and then took the sum of it and then use the sigmoid function. So this way we can calculate all the neurons of the hidden layer. Now the next task is to calculate the weights, and we will have to calculate those weights that are optimum. So we will see in the upcoming slide how can we calculate the optimum weights. But that is how you calculate the neurons of the hidden layer. Now once all the neurons are calculated, we can write it in the form of vector as shown here. So you can see that each of the neurons from previous layer is contributing to calculate the activation function for each of the neurons in the next layer. Also, as I said earlier, the weights used in calculating each of the neurons are different. So in every layer we have a weight matrix that is to be calculated, and then we will use that weight matrix to calculate the neurons of the next layer. So that is how neural network functions. And obviously we will not be doing this manually. But this was just to give you an idea to explain how neural network do the calculations. Now coming back to the calculation of weights. So as I said earlier, we have to find those weights that are optimum. So let's see how we can calculate those weights. Now weights are nothing but coefficients. So we must have a cost function to guide us to calculate the best possible weights. So as you can see on the screen, the cost function is similar to logistic regression function with some modifications. Now you can have a look at it. All the notations are given here. Well, to be frank, it looks a bit scary, so I'll not be going into details. But just understand that the entire cost function is similar to logistic regression, and we have just added a regularized parameter. Hence, this is called as regularized cost function. Now refer to the note given here. It says that regularization is a technique used for tuning the function by adding an additional penalty term in the error function. The additional term controls the excessively fluctuating function such that the coefficients don't take the extreme values. That is the basic purpose of regularization parameter. So this was the cost function of neural network. Now just to avoid confusion, let's quickly revise what we have covered so far. So neural network basically mimics the human brain to identify the patterns. Then we have components of neural network, which are input layer, hidden layer, and the output layer. Input layer contains the feature, hidden layer contains the activation function where all the calculation takes place, and output layer contains the output. Then we saw the activation function. So the purpose of activation function was to calculate the neurons. And we saw that activation function that we use was sigmoid function. Also, there are different activation functions available, and the choice of activation function will affect the final outcome. Then we saw how weight matrices are assigned to each of the neurons, which is used for calculating the activation function. Now for calculating the activation function, we use weight matrices. So for each of the neurons, there are different weights assigned. So we multiplied the weights assigned to that particular neuron by all the neurons in the previous layer. And that is how we calculate the activation function. Then we saw the cost function that we use to calculate the optimum weights. So in the cost function, we saw that cost function is similar to logistic regression, but we have introduced a regularization parameter so that it prevents the coefficient from taking the extreme values. That is what we have learned so far. So keep this in mind because we'll come back to this slide again and expand it further as we move along. Now let's see the steps involved in a neural network. So the steps that I'm going to explain are a very simplified approach, and it can be extended over more complex problems. This is just for understanding the working of the neural network. So let's see what are the steps involved. In step 1, we initialize the weights. Let's say wij at some random values in a small neighborhood around 0. Then in the next step, we use the forward propagation to compute the activations of neurons in all the layers. That is the vectors A1, A2 up to AL. Remember the number in superscript denotes the layer. Now don't get overwhelmed by the new term forward propagation. The method that we saw earlier of calculating the activation function using neurons from the previous layer is called as forward propagation. This is nothing but a fancy name, that's it. Then we'll have to calculate the weights using backpropagation such that the loss function is minimized. Now this is a crucial step, and I'll be explaining this in a bit. But before that, let's see what are the other steps. Then in step 4, we will update the weight matrix for all the layers. So whatever weights we have calculated in step 3, we will use those weights and update our weight matrix using those weights. Then in step 5, we'll go back to step 2 again until convergence which is attained when improvement in the next iterate is negligible. So these are the basic steps involved in a neural network. Now, as I said earlier, the step 3 is a very important step. So let's see this in a bit more detail. So in the first step, we initialize the weights wij at some random values in a small neighborhood around 0. So here weights are being denoted with wij, but earlier we used the notation as theta ij. So both are same, there is no difference in it. You can even write theta ij here. Then in the second step, we will use the forward propagation method to compute the activation of neuron in all the layers. That is the vectors A1, A2 up to AL. Now don't get confused by the new term forward propagation. The method that we saw earlier of calculating the activation function using neurons from the previous layer is nothing but forward propagation. So we have already studied this forward propagation method. Then in the third step, we will have to calculate the weights using backpropagation such that the loss function is minimized. Now this is a crucial step and I will be explaining this in a bit in detail. But for now, see the next step first. Then in the fourth step, we will update the weight matrix for all the layers. And then we'll go back to step 2 until convergence which is attained when improvement in the next iterate is negligible. So we keep on doing this until improvement in the next step becomes negligible. So these are the steps involved in building a neural network. Now as I said that step 3 is a crucial step. So let's see step 3 in detail. So we use backpropagation algorithm to calculate weights. Now the goal of backpropagation is to adjust each weight in the network in proportion to how much it contributes to overall error. Basically, if we reduce each weight's error, eventually we'll have a good prediction. So while performing the backpropagation, we need to compute how good our predictions are. So to achieve this, we use the concept of loss function or cost function. Now depending upon the problem, we select the loss function. One loss function is the MC, sum of squares of the differences between actual and the predicted value. Now the next question is, how do we reduce the loss function? Because our predictions are only good if we have the optimized loss function. So to optimize the loss function, we use another algorithm which is called gradient descent algorithm. Gradient descent algorithm reduces the weights by changing it such that the loss converges to the lowest possible value. So we try to reduce the loss in a controlled way. We take small steps towards the minimum loss. This process is called as gradient descent. The equation shown here on the screen is for the loss function, and the graph given here is showing the loss function being converged to the minima in a stepwise fashion, which is called gradient descent. Here alpha is known as the learning rate and it is multiplied by the derivative of our loss function. So we have taken a partial derivative of the loss function here. Now in partial derivative, we find the derivative with respect to a particular term and keep the remaining terms as constant. So as you can see, we have taken a partial derivative of loss function. In partial derivative, we find the derivative with respect to a particular term and keep the remaining terms as constant. To calculate the partial derivative of a function, we use chain rule of derivatives. We don't have to go into the details of it. It is just simple maths. So that is how we use gradient descent function to converge a loss function to the minimum. Well, I hope this has become clear now. I have explained it in a very simple way, but in reality it is a complicated process and a lot of things happen in these steps. But this is enough for us to know. We don't have to go into more details because everything will be done by R, but we should at least know the basics and we should know how things are happening in the background. Now the next question is, how do we initiate the weights? So we initialize the weights by random initialization in a small neighborhood around 0. That is an interval of the form minus epsilon to plus epsilon, where epsilon is generally a small positive number. Then the termination or convergence criterion is when the absolute improvement in the next iterate for all the weights is less than 10 raised to the power minus 4. Then we introduced another term called momentum. So it has been observed that the step of updating weights can be made more powerful if we add a fraction of previous weight adjustment. This is known as momentum. So in our weight formula, we add a term eta multiplied by previous weight adjustment. Eta will always lie between 0 to 1. So that is how we introduce the momentum term. Now the purpose of momentum component is to move the weight adjustment to stay in the same direction, which in turn increases the rate at which the weights approach the neighborhood of optimality. So in short, momentum expedites the process of optimization. Okay, so now again, before moving forward, let's quickly summarize what we have covered so far. Previously, we summarized these 3 topics that we had covered earlier. Now we have covered the 5 steps involved in building a neural network. So the first step was to initialize the weights. We initialize the weights in a small neighborhood around 0. Then we calculate the activation function. We use the forward propagation method. Forward propagation method was nothing but the method that we saw earlier for calculating the activation function by using the neurons from the previous layer. After that, we used backpropagation algorithms to calculate the weights. So this was the step 3 that we had discussed in detail. I'll summarize that as well. Then in step 4, we update the weights. And then in 5th step, we repeat this process from step 2 until the convergence criteria is achieved. So this was in short the 5 steps that are required to build a neural network. So the step 3 that we had discussed in detail had 3 things: backpropagation, loss function, and gradient descent. Now the goal of backpropagation was to adjust each weight in the network in proportion to how much it contributes to overall error. So basically, if we reduce each weight's error, eventually we will have a good prediction. So that was the whole idea for using backpropagation. Now while using the backpropagation, we needed a measure to know how good our predictions are. That is the reason we use loss function or cost function. Now depending upon the problem, we select the loss function. One common loss function was MSE, which is the sum of squares of the differences between actual and the predicted values. And then to optimize the loss function, we used another algorithm that is called gradient descent algorithm. So gradient descent algorithm tried to reduce the loss in a controlled way by taking small steps towards the minimum loss. This process of taking small steps towards the minimum loss is called as gradient descent. We also saw the graph of gradient descent, where the function was being converged to the minima in a stepwise fashion. Then the next question was, how do we initiate the weight? So we initialize the weights by random initialization in a small neighborhood around 0. This small neighborhood is an interval of the form minus epsilon to plus epsilon, where epsilon is generally a small positive number. Then we introduce another concept called momentum. So it has been observed that the step of updating weights can be made more powerful if we add a fraction of previous weight adjustment. This is called as momentum. So we saw the equation where we added a term eta and we multiplied it by the previous weight adjustment. And this eta always lies between 0 to 1. So basically the purpose of momentum was to move the weight adjustment to stay in the same direction, which in turn increases the rate at which the weights approach the optimality. So basically it expedites the process of finding the optimal weights. So that is what we have covered so far, and I hope that the things have become clearer now. Now we will move to the next topic. The next concept is gradient checking. Although we saw a very simplified approach for understanding the backpropagation, but in reality backpropagation is an algorithm with a lot of details, and it could be tricky to implement. So at times it seems that we are going in the right direction and cost function is decreasing. But there may be some bug in the implementation and we might end up with high level of error. Hence we introduce the idea of gradient checking, which ensures that we are going in the right direction. So if you see the graph here, we know that derivative is nothing but the slope of the curve at a particular point. So if we want to calculate the slope of the curve at a particular point, we will calculate its derivative. Now to calculate the derivative, we draw a tangent on the curve and then simply calculate the slope of that line. So as shown here, slope of line 1 is nothing but the derivative of j theta at point theta. Now slope of line 1 can be approximated by slope of line 2, which is adjoining 2 points on the curve as shown here. So why are we doing this? Because it is easy to find the slope of line 2 compared to slope of line 1. And the slope of line 2 can be considered an approximation of slope of line 1. So it is better to find the slope of line 2 because it is easier. Now the 2 points on line 2 are nothing but theta plus minus epsilon. And epsilon is generally considered as 10 raised to the power minus 4. Hence we can write the derivative as j theta plus epsilon minus j theta minus epsilon divided by 2 epsilon. Similarly, if there are more than one variables, we can extend the same concept and we'll use partial derivative there. Recall, partial derivatives are also derivatives but taken by making other variables as constant. So this is known as numerical approximation, and this is how gradient checking is done. Now the idea of gradient checking is to check if the derivative terms computed by backpropagation are approximately same as the one computed using numerical approximation. However, numerical approximation is computationally slow. So what we do, we compute derivatives for few iterations. Let's say maybe up to 5th iteration. So up to 5th iteration, we use both numerical approximation and backpropagation. After that, we check if partial derivatives at the initial weights are approximately same from both the methods. Then we turn off the gradient checking and execute only the backpropagation. Because now we know that we are moving in the right direction. So that was the whole purpose of gradient checking. It guides us in calculating the optimized weights. Now, one of the drawbacks of neural network is that there is no direct way of translating the weights into a compact set of decision rules. What it means is, we don't know which variable has more influence on the network. So we carry out sensitivity analysis to know how the relative importance of the variables are. So we'll not go into the details of it. I'll just give you an idea about it. So we vary certain features from their minimum to their maximum and check their effect on the output in comparison to other features. And this is how we derive the importance of the variables. Now this is just to give you an idea about sensitivity analysis. You don't have to go into the details of it right now. However, if you wish to know more about it, you can explore it on internet. So now before wrapping it up, let's quickly summarize what we have covered after the previous summary. So all these concepts we have already covered and we have already covered their summaries as well. And after this we learned a concept called gradient checking. So in gradient checking we learned three things. Why do we use gradient checking? What is gradient checking? And how do we implement gradient checking? So the purpose of gradient checking is that the backpropagation algorithm in reality is a very tricky algorithm to implement. And at times it seems that we are going in the right direction and our cost function is decreasing. But in reality, there may be some bug in the implementation and we might end up with high level of error. So gradient checking is a method that ensures that we are going in the right direction. So that is the reason we use gradient checking. So in gradient checking, we saw the graph where we learned to calculate the derivative. Derivative is nothing but the slope of the curve at a particular point. So we calculated the derivative by drawing a tangent on the curve and we calculated its slope. So we saw this entire process. We also learned that in case of more than one variable, we will have to use partial derivative. Partial derivatives are nothing, but they are also derivatives taken by making the other variables as constant. And this entire process of gradient checking is known as numerical approximation. Now gradient checking is computationally slow. So we don't use gradient checking for the entire process. Instead what we do is we compute the derivative for few iterations. Let's say for 5 iterations using both the methods, gradient checking and the backpropagation algorithm. And then we check if the partial derivatives from both the methods are same or not. If both the methods give the same result, then we turn off the gradient checking method and execute the entire problem using the backpropagation method. Because now we are assured that we are going in the right direction, and hence we turn off the gradient checking method. So that is all about gradient checking. After that, we briefly covered the sensitivity analysis of neural network. So we do sensitivity analysis to know the relative importance of the variables. Basically, to implement the sensitivity analysis, we vary certain features from their minimum to their maximum and check their effect on the output in comparison to other features. And this way we derive the importance of variables. So this is in short what we have covered on sensitivity analysis. So I hope guys you are able to connect the dots now and you are able to make sense of all the slides that we have seen earlier. And with this we have come to the end of this section. So I know guys it was a lot in terms of maths and concepts, but you need to appreciate the fact that this is one of the most powerful technique. So this was just a tip of the iceberg. You have understood the functioning and concepts of it, and now you can build upon it further as you progress. So the concepts and the fundamentals remains the same. Also, the neural network that we have seen in this section is called as artificial neural networks, often denoted as ANN. Now there are other types of neural networks as well, such as recurrent neural network, which is useful in a time series data, convolutional neural network, which is specifically useful for images and videos. However, the principles in all these neural networks remain the same, and sometime later in future we can explore them. Anyways, let's see what we have covered in this section. We discussed why neural networks should be used. Then we saw what is a neural network. After that, we saw activation function in neural network. Then we learned cost function of neural networks. Then we discussed steps involved in neural network. Here we also discussed about forward feed, backpropagation, and gradient descent algorithm. Then we discussed about a concept of gradient checking, which helps us ensuring that we are heading in the right direction. Then to know the importance of variables, we touched upon the idea of sensitivity analysis. So that was all that we had covered in this section. And now the next step is to do assignments in R. So we will do two assignments, one for classification and the second one for regression. So alright then, I'll catch you up in the next video now.